Let's begin by considering the loading effect on the analog output channel, as indicated here. I'm measuring the actual voltage being produced by the analog input channel 0. And I'll hide these so we can just concentrate on the intended analog output voltage. We can operate with the slider here. We then observe the actual analog output voltage on the right side. So you'll notice we can sweep through the full range of -10 to +10 volts and everything looks fine. I'll begin by introducing a light load of 10 kilo ohms. And again, you notice that the green slider on the right basically tracks what we are trying to accomplish. A moderate load of 1 kilo ohm, suddenly we notice that the actual analog input voltage never gets higher than about 2 volts. No matter how we operate the desired or intended voltage, we'll always seem to be limited to about a range of -2 to +2 volts. Now, if we take that maximum value of 2.29 volts and divide it by a kilo ohm, we get just over 2 milliamps for our maximum current drive. Now, consider a heavy load, which is 270 ohm resistor and some LEDs. You'll notice that we don't get above 2.5 volts, and the LEDs glow only fairly weakly at best. Now, the voltage follower provides us the ability to generate a replica of our input voltage, but yet draw 0 effective current from the analog output. The voltage follower is able to produce whatever current is needed by the load to sustain the desired voltage. So I have the voltage follower circuit implemented here. We use the ±15 volts for myDAQ. This is the same collection of signals we were looking at earlier. And then I take the voltage follower output and use that to operate the heavy load. Again, the thing to note here is that the actual voltage being developed on the analog output is exactly what we want. And since the voltage follower copies that to the load, that means that's the voltage we're actually delivering to the load.